Hi there, hope you're having a wonderful day, because I am, and you should too. So lately, flat earthers have been crowing, they've been hanging from the rafters, screaming at the top of their lungs that the upcoming solar eclipse on the 21st of August is impossible with the heliocentric model, and that somehow it proves that the flat earth model is valid. Pardon me. How that is, I don't know. So, if you can leave me a comment in the comments section with the details of how the upcoming eclipse makes the flat earth model more plausible, I would greatly appreciate it. If you do, thank you in advance. Moving right along. So, what am I going to do in this video? Well, we're going to have a look at the flat earthers' argument as far as this eclipse is concerned and what they're actually talking about. Then we're actually going to look at the numbers, make a few calculations, and come to a conclusion. And I would say by the time we get to the end of this video, by the time we get down to the bottom of this page here with a pair of numbers here, you will realise that what the flat earthers are claiming is incorrect, and that not only does this eclipse fit or even be possible on the with the heliocentric model, it will fit the heliocentric model like a glove, like it's meant to be there, like it actually is. So let's move right along and find out what flat earthers are actually saying. So, the official story on this upcoming eclipse on the 21st of August is that the shadow, and you can see little animations of this, the shadow is going to travel from west to east across the surface of the Earth, right through North America. Now, the flat earthers are claiming that this is impossible on the helio or with the heliocentric model, and that the shadow should actually travel from east to west. The reason for this is a combination of two things. Number one, the orbital speed of the moon, which happens to travel in an anti-clockwise direction, along with the rotation of the Earth, which is anti-clockwise also. But the orbital speed of the moon is 13 degrees per day, roughly. And the rotation speed of the Earth is actually 360 degrees a day. This discrepancy is why flat earthers are saying that despite the fact that the moon is travelling very slow between the Earth and the Sun as the eclipse occurs, that the actual rotation speed of the Earth travelling this way will cause the shadow to appear to travel across the surface of the Earth in the opposite direction from east to west. I can understand what they're saying, that as the continents are shifting this way, because it's moving so slow in the same direction, that it'll actually look like it's going in the opposite direction on the surface. So let's move on to the data. So what we've got here, and I went ahead and actually done a lot of this ahead of time, so you don't have to deal with any of it. And any of the information, you can look it up and actually confirm it. I'm just going to have a quick drink. So, what I did, I went ahead and worked out the time that it takes for this solar eclipse to actually start and finish. And when I say start and finish, I mean from the point that the penumbra actually touches, that is the first bit of the moon's shadow, actually touches the western side of the Earth, to when it actually just leaves the eastern side of the Earth. So it's the totality of the eclipse even touching the Earth at all. So we've got a start and finish time that they've got details of that you can look up in many places on the internet, and it works out to be 5 hours and 20 minutes, or 5.33 hours roughly. So in that time, we need to work out how much the Earth rotates. So basically, we grab our calculator, and I've already done the calculation there, but I'll show you how I've done it. So basically, we need to work out how many degrees are in this 5.33 hours of rotation of the Earth. How many degrees does the Earth rotate in 5.33 hours? So 360 degrees in a full rotation. Now, and a full rotation occurs over a period of 24 hours on the Earth. So we divide 360 by 24 and it equals 15 degrees per hour. And we multiply that by 5.33 because it's 5.33 hours. And we get 79.95 degrees. Now we can work out how much surface of the Earth, how much of the, say at the equator, the actual distance or length of Earth that covers using the circumference of the Earth. What we need to do is divide 40,075 kilometres by 360, and we get 111.3, which isn't really an important number for us. Then we multiply that by 79.95. And we get 8,899. Now, that isn't the distance that the shadow covers as far as the disk of the Earth is concerned. When I talk in this context where you just see the Earth like that, this is the actual distance it travels in an arc, as in the surface of the Earth being a ball at the equator. Now, from this edge here to the centre of the Earth, as in like if I drew a line through the middle of the disk of the Earth, if we're a long way away from it, that would be 90 degrees there. We have 90 degrees on this side, 90 degrees on this side to the edge, and then on the back side we have another 90 degrees to the line on the opposite side around the back side, and another 90 degrees on the back, and that's how we get our 360. So during that eclipse, the Earth has moved around this way, not quite to that middle line. It's probably gone to about here somewhere. So it's travelled from this edge around to there. That's how far it's actually travelled in that time. If you talk about where the shadow starts on the surface of the Earth and the Earth rotating during that eclipse, the Earth actually only travels to this spot here. You can work that out for yourself, as I just did. So let's work out how far the moon actually travels in that time. So how far does the moon travel in that time? Well, to do that, we need to know how far or how long it takes the moon to do an orbit. And the orbital speed, or the orbital period for the moon, is 27.323 days. So, $360 divided by, because 360 degrees in a circle, which is what an orbit is roughly, divided by 27.323 equals 13.175 degrees per day. Now we need to work it out per hour. So we divide it again by 24 and we end up with 0.54. So that's per hour 0.548 degrees. Now we need to multiply that by this number up here, which is our number of hours that the eclipse occurs over. So we multiply that by 5.33 and we end up with 2.926 degrees. Now where is it? There. It is 2.926. Should have left myself a little bit more room there. And now we need to work it out in kilometres. So according to the books, the moon is, we'll call it the radius, but it's the distance from the Earth, is 385,000 kilometres. So using those numbers, we can work this out using pi. So 385,000 times 2 to get the diameter because it's actually the radius. And then we need to multiply that by pi. We get that, it's like 2,419,026. And then we divide that by 360 because that's the whole circle. Okay. Then we multiply it by 2.926 to get the amount that it moves inside this time here. And that's our number there. That's how far that shadow moves, or how far the moon moves in that period of time. But there's more to this than meets the eye. Because, and I'll put this number up here, we need to go back and look at another drawing. Actually, this one here. So what's actually going on is, as the eclipse starts, we'll say this is the Earth, and as you can see, this is not to scale. Sun, and this is the moon before the eclipse. This is the moon after the eclipse. So, if you look here, here's the front edge of the moon that's going to create the first shadow on the Earth. Now, as the moon travels through, you'll notice that that front edge is now up here, and the diameter of the moon is actually part of that whole movement in obscuring the Earth. Now, while that is the distance that the moon travels, and I should put that down, this is part of something that I'm going to do next that's going to show that not only is the eclipse possible on a heliocentric model, it fits it like a glove. So, it's 19,661.3 kilometres. So the moon travels 19,661.3 kilometres during the eclipse. The Earth's surface travels 8,899.9 kilometres during the eclipse. So in fact, the moon travels twice the distance of the Earth's surface during that eclipse. So what flat earthers are saying isn't entirely true. The moon actually travels further than the Earth's surface during that eclipse. And in fact, what you're going to find is that number there is more, way more, than Earth's diameter, which is basically from west to east, from one edge to the other edge, is the diameter of the Earth. And the moon has travelled many times more than that distance. Well, not many times, but it's probably 1.5 times that distance. So the moon easily has gone over the distance of the width of the Earth, and the Earth has only rotated a fraction of its circumference. Not even a quarter of its circumference has it rotated, yet the moon has completely covered the distance across the Earth. But that's not the end of the story. So we've just confirmed that yes, in fact, the moon has covered more than the distance in this time of the diameter of the Earth, and the Earth's surface travel is only 1/4 of its circumference. Which means that, just what I said back here, when the eclipse starts, we mark a point on the surface of the Earth. And that's the point where the eclipse shadow first touches the Earth. By the end of the eclipse, the back of the shadow is just leaving the eastern edge from west to east, and the Earth has only rotated to that point there roughly. But that's not the end of the story. Now we need to show that not only is the eclipse plausible, which we've just proven on the heliocentric model, but it fits it like a glove. So there's one other thing we need to account for, and that is the angular size of the sun. You see, the angular size of the sun causes the penumbra, and the penumbra causes the moon to actually have to travel a little bit further to not cast a shadow, or to start casting a shadow. And it is the angular size of the sun that causes the penumbra. As you can see, if I go from one edge of the sun to the opposite edge of the moon, we get that flaring effect. Now, bear in mind, the sun is 389 times further away than the moon is from us, 149.6 billion kilometres. Those rays from the sun are going to be travelling near parallel. So we don't really need to consider that the rays, or account for the rays actually going out and sort of diverging away from the sun or converging towards the sun from our perspective. They are nearly parallel. So we can use this to our favour and just take away the angular size of the sun from the equation to take the penumbra out of our calculation, out of our 16,187, to get what should be a close number to the diameter of the Earth. So considering that the Sun and Moon have the same rough apparent size to us on Earth, which is about 0.5 degrees, and the point at which we need to take it away is actually luckily where the distance of our object that's casting the shadow is, it's really easy. So if we go back here, we can see the angular size of the Moon is 0.5 degree and the Sun is 0.5 degree also. So we can just take away 3,474 from this figure here. So 16187.3 minus the diameter of the Moon again, which is actually the angular size of the Sun at the Moon, relatively speaking, from our point of view. 3,474 equals 12,713.3. So there's the stated diameter of the Earth, 12,742, and here's the figure I got, 12,713. So it's only about 30 kilometres off. That's not very much, and I've actually done this actual set of calculations earlier today, and I went to a couple more decimal places and it actually got a little bit closer. It was only about 20 kilometres off the last time I'd done it. So this shows that not only is this solar eclipse possible on the heliocentric model due to the fact that the Moon travels, more than twice the distance that the surface of the Earth does in the same amount of time, in our 5.33 hours, but that using the data from the eclipse and the existing data, some of the existing data in relation to the Moon and the Earth and the angular size of the Sun, things that we can all see and calculate or work out or measure, we can see that I've managed to get within 30 kilometres of the Earth's diameter using the data from the solar eclipse. This shows that not only is the solar eclipse possible on the heliocentric model, but shows that it is more than likely 100% a fact that the heliocentric model is the model that we are living in. It is the way that things are. And the fact that I can calculate very closely the Earth's diameter using data from the eclipse just proves that that eclipse is 100% possible on the heliocentric model. Have a great day. I'll catch you later.